Alright, so in this video we are going to take a look at the alternating groups for n greater than or equal to 6. And we're going to show that an is simple. Which means that if you have a normal subgroup in an, then either it's the trivial subgroup or it's the whole group. We've discussed this briefly, but an is supposed to be the set of even permutations. And a good reminder of what that means is that every permutation can be written as a product of disjoint cycles. For instance, 1, 3, 5, 2, 4, 7, 6, 8, 9. But it turns out you can decompose cycles into products of transpositions. So this cycle is equivalent to 1 times 3, and let's see if I can get it right. 3 goes to 5, 2 goes to 4, 4 goes to 7, 6, 8, 8, 9. And you can see that they're an even number, even number of transpositions, so this is actually in the alternating group A9. And so one of the theorems you prove in a lower level modern algebra course is that if you write a permutation as a product of transpositions, then R is congruent to K mod 2. And so that there's this nice, let's see if I can state it properly, that there is a nice subgroup consisting of the even permutations, where you have an even number of transpositions, and that's defined to be an. Now, of course, normally in a modern algebra course, this is introduced very early on in the course before homomorphisms are introduced. But with the concept of homomorphisms, there's an easier way to define it, and that's what I'll do next. Namely, given any permutation on Sx, well, let's just do Sn to make this easier. You can consider r to the n, and you can consider the transformation from r to the n to r to the n given by taking the vector x1 through xn and permuting the coordinates. So for instance, a sigma where the permutation 1 goes to 3 goes to 2, and x is a vector in R3, so let's just say 5, negative 1, 2. Then sigma x, well, we're going to send the first coordinate to the third coordinate. We're going to send the third coordinate to the second coordinate. And we're going to send the second coordinate back to the first coordinate. So in particular, this is a linear transformation. And it's not hard to show it's invertible. And so this defines a homomorphism from Sn to the general linear group of n by n matrices over R. And why would I care about that? Because then there's also another homomorphism called the determinant. That we're familiar with. And so there's this composition of homomorphisms, which I'm also going to call the determinant for simplicity. And it turns out you can prove that the determinant of a permutation is just negative 1 to the k, where k is the number of transpositions in a decomposition of sigma as a product of transpositions. And why would that be true? Well, because you're talking about a homomorphism. So if I've rewritten sigma as a product of transpositions, then the determinant factors through the product. And it's not hard to show that the determinant of a transposition has to be -1, and since there's k terms, you get -1 to the k. And so then you get that lemma from modern algebra for free, because if you have two different factorizations, well, one of the determinants is -1 to the k, the other one's -1 to the r, and so k and r have to be congruent mod 2. Of course, why is it the case that a transposition has determinant 1? Well, the easiest way I can think of to argue it is that you can prove that every transposition is a conjugate. They're all conjugate to each other. So they're all conjugate to the transposition 1, 2. So the determinant of this transposition is equal to the determinant of 1, 2. The corresponding matrix there is that one. It's one of the elementary symmetric matrices you study in linear algebra, and you prove in linear algebra that the determinant of that matrix is -1. And so, voila, the determinant of a transposition must be -1, and so you do get this result. More importantly, the kernel of this map is the alternating group. It's those permutations of determinant 1, which under this fact means it's those permutations that can be written as an even number of transpositions. Okay, so now we do the proof. Why is a n simple? For n greater than 5? Well, let's do induction on n. Base case, n equals 5. Good news, we already did that. So we only need to do the inductive step. So in the inductive step, we're going to let n be greater than or equal to 6. And so we're going to let capital N be a normal subgroup of an, and we're going to assume it's not the trivial subgroup. Then what we want to show is that this normal subgroup is all of an. So the textbook does proof by contradiction, but you can actually do a direct proof. There's no need to talk about contradiction. We just need to show that n is equal to an, and that's good enough. So sometimes you see this. People talk about doing a proof by contradiction, but then at the end of the day, you check and you realize you didn't actually need to use the word contradiction at all. You could have just done a direct proof and save yourself a few sentences. All right, so we want to show that this normal subgroup is equal to this whole group. How are we going to do that? Well, we proceed in stages. So I'm essentially presenting the proof from the book, but I'm doing it in reverse order. First, what I'm going to claim is that there's a permutation in n that fixes the number little n. I mean, at the very least, we already know there exists a permutation in n that's not the identity permutation. Oh, but this also has to be not the identity permutation, otherwise this idea doesn't work. Why do I want this claim? Well, because I want to apply induction. And so what I can do here, if I knew this claim was true, is then I now know that and intersect the fixed points of this element. This element. Is non-empty. What do I mean here? I'm identifying a sub n minus 1 as the group of alternating permutations that fix this. Although one should be a bit more accurate, they're a little more careful in the book. Let's just call G to be an, and then this is G sub n because G acts on the integers 1 through n in the obvious manner as permutations. And so with that definition, this is the stabilizer subgroup. This also explains part of the reason why this stabilizer notation is kind of poorly chosen, because we use subscript element, and here the subscript element conflicts with the subscript n here. But by doing things this way, hopefully there's no confusion. The point is, here's this stabilizer subgroup, those permutations that fix n. They intersect n non-trivially. This is isomorphic to a smaller alternating group by one of the isomorphism theorems. This is a normal subgroup of Gn. And so by induction hypothesis, since G sub n is a smaller alternating group that's still bigger than 5, we can conclude that n intersect Gn is equal to Gn, which would tell us that Gn is a subgroup of our normal subgroup. So this approach allows us to apply our inductive hypothesis, and that's what we're going to do. So why is this claim true? Well, it's going to boil down to cases. And so the cases are, there exists at least some permutation. It's going to have a cycle involving the symbol n. The next element in the cycle is going to be some element a. And we're going to have different cases. One of the cases is that there's other elements on the cycle. The cycle's length at least 3. And then there's a bunch of other cycles that I'm not going to be concerned about. But the point is that the cycle containing n has length at least 3. Suppose that is true. Well, we're assuming n is at least 6. So we're going to assume that we have at least 6 other elements to work with. So I'm going to let tau be n, a, b interchanges with some other element x, and y interchanges with some other element z. And I'm going to look at tau sigma tau inverse. By definition of how conjugation works, this permutation is going to have n, a, and it's going to replace b with x. And that's going to have other stuff. And then other stuff. But the point is, because we're closed under conjugation, this permutation is in n. And so I can also invert it and multiply it by sigma. So let's invert it and multiply by sigma. So now let's look at the calculation sigma inverse times tau sigma tau inverse. N goes to A goes back to n. So congratulations, that's a fixed point. These two permutations are both elements in n. This product is also in n. So if I let pi be this permutation, then pi is an element of n. And so I did what I wanted to do. I found a non-trivial permutation that fixes the element little n. But I had this assumption. So what happens if this assumption is false? Well, what could possibly happen? The other case would be that our permutation n was part of a 2-cycle. Who knows what else there is, just that's true. Well, again, I can let tau be, well, let's just take any 3-cycle not involving A. Then you see conjugating by tau is going to leave that 2-cycle alone. And it's going to conjugate the rest. In particular, it is actually going to change the permutation somehow, because somewhere x, y, and z is going to appear. Unless, of course, x, y, and z are all fixed points of sigma. But because sigma is an even permutation, and we have this disjoint cycle, it must be the case that there must be some other element number that is not a fixed point. And so pick that element to be x. So then you're guaranteed that you had some cycle that had x. Who cares what else? Oh, let's just put y, just because we can. And then now in the new cycle, it's got y, comma, z. So you can see that it is in fact different than sigma. With one possible exception. The one exception you have to worry about is if you're dealing with the 3-cycle x, y, z itself. But, I mean, if there's something here and the cycle's length bigger than 3, just don't pick z. Don't pick z to be that element. And if you're in the rare case that you don't have an option there, that you have a cycle of length 2, you have to have a cycle of length 3, and there's no other options, then congratulations, it looks like your n is equal to 5, and you've got an odd permutation, so that's a contradiction. Ergo, it must be possible to, even in this strange case, to pick a choice of z so that you actually manage to get a conjugation, a conjugate that's not sigma. That's a little more complicated than the way the textbook does it, so you can try the textbook's approach as well. But, this is the idea behind what I'm doing, is trying to reason from first principles, whereas theirs is the cleaned up version after already figuring out what you're supposed to do. Anyhow, this same exact trick works now, because you now have a permutation, 2 distinct permutations that change the value of n to another fixed value. So when you invert one of them and compute and multiply them together, it makes n into a fixed point. So we now have a permutation in n, the normal subgroup, that fixes the number n. And as discussed, this forces the stabilizer subgroup of n to be a subgroup of our normal subgroup. So what more can we do? Well, Gn, the stabilizer subgroup, is not a normal subgroup. So in particular, all these conjugates are distinct, or potentially distinct. And since n is closed under conjugation, what we get from here is that since Gn is going to be a subgroup of our normal subgroup, then all these conjugates are as well. And so, remember, this is the permutations that fix n. It's not too hard to see what happens when you conjugate. Let's use tau here. Well, you end up getting sigma of tau of n equals n. Wait, wait, hold on. Right, let me do this more carefully. So suppose you have something in here. That means that tau inverse sigma tau is in Gn, which means that tau inverse sigma tau of n is equal to n. Which means sigma tau of n is equal to tau of n. Okay, I now verified the thing I thought was true. And you can prove vice versa. When this happens, work backwards, multiply both sides by tau inverse. You now see that this conjugate of sigma sends n to n. That tells you that this conjugate of sigma is in the stabilizer subgroup, which tells you that sigma lies in this other conjugate. In particular, this tells you that we get this fact. It's a stabilizer subgroup of a different point. And in particular, that tells us that G sub I is a subgroup of n. Because certainly you can find a permutation that sends n to I. And fixes anything else. I mean, an even permutation. So that when you do this conjugation, you get G sub tau of n to be I, G of I. And so congratulations, not only is one of these stabilizer subgroups contained in our normal subgroup, they all are. Which means that the largest subgroup containing all of them must be a subgroup of our normal subgroup. And so then the result follows from pointing out that that's actually just all of an. So that's all we really need to show in order to finish this claim. So why should that be true? Well, I mean, take a sigma and an. You must be able to write it as an even number of transpositions. Pair them up, and then notice that sigma 2i, sigma 2i plus 1 must fix an element. In particular, it must be in G sub j for some j. Why? Because when you multiply two transpositions, you're either going to get a 3-cycle or two disjoint 2 cycles. And since n is at least 5, you're permuting at most 4 elements, there must be a fixed point. And so you've written it as a product of things that each belong to one of these sets. It must be the case that sigma is in this smallest possible subgroup containing this set of stabilizer subgroups. And of course, an is the whole group. So you're saying an is now officially a subset of this thing, and yet by definition an is one of the possible options, therefore you must have equality. What I mean there is that there's a theorem that the subgroup generated by a subset is the intersection of all groups containing the subset, this is one of the terms in that intersection, we now have shown it's a subset, therefore it is the intersection. So there we have it, a proof by induction that the alternating group is always simple. The textbook also notes the other traditional approach is to prove that the alternating group is generated by 3 cycles, and then to show that every normal subgroup would have to contain at least one 3-cycle, and hence every 3-cycle. I'll indicate at least some of the ideas of that proof, because we're actually halfway there anyways. Namely, what we've just shown was that the smallest subgroup generated by all these stabilizer subgroups is the whole group. Well, by induction, GI is generated by 3 cycles. For n greater than or equal to 3. The base case is trivial. A3 is the cyclic group of order 3. And so for n greater than or equal to 4, you use this fact. And so in particular, GI that's what we mean by generated. It's generated by the set of all permutations of the form sigma, where sigma is a 3-cycle, the form a comma b comma c. A, b, c are integers. We're excluding I because we're in the stabilizer subgroup. By induction, we're assuming we're generated by that. Well, I mean, suppose that you have a group generated by a bunch of subgroups, and H1 is generated by a set S. I'm sure you can guess that you can replace H1 with S. It's worth pointing out that technically what this phrase means is that you're taking the union of all the elements of these subgroups. So you get all these 3 cycles, and that includes every 3-cycle in the full group, because every 3-cycle has to lie in one of these sets to begin with. So you get for free that the alternating group is generated by 3 cycles. So the alternative approach is supposed to say you let n be a normal subgroup of an, and you want to claim n contains a 3-cycle. Then you show n contains every 3-cycle. And then you declare victory, because you just showed that an is generated by all 3 cycles. So if you have every 3-cycle, you must be an. And so the reason the textbook authors chose not to do this proof is because this first claim is actually a pain in the neck. Going from here to here is similar to the same technique the textbook uses, where you use a lot of conjugation arguments. Once you have one 3-cycle, use conjugation to get all the others. But showing that you have at least one 3-cycle is kind of difficult. It's also clear that the condition that n has to be at least 5 has to pop up somewhere, because there is a normal subgroup in A4, and the non-trivial normal subgroup in A4 is the one that has no 3-cycles in it, the Klein 4 group. And it's worth pointing out this implication to this one actually holds as soon as n is at the size of n is at least 3, which is why when n equals 4, the only counterexample has only 2 cycles. So this is the part we want to prove. We want to prove that if you have a normal subgroup in an alternating group where n's at least 5, then you must have a 3-cycle. It goes in stages. So again, the idea is you're going to take a non-trivial permutation and you're going to break it down by a bunch of cases. And in each case, you end up showing that there's a 3-cycle. The first case is sigma has, when you write it as a product of disjoint cycles, one of the disjoint cycles has a long length. So let's just write it as A, B, C, D and continue it all the way up to whatever the last element is. Let's call it Z. Then it turns out if you conjugate by the right permutation, and multiply by the inverse, you're still going to be an n, but you want to get a 3-cycle, and it turns out the right choice is to conjugate by ABC. And what you'll end up getting is ABC. And so the point is, if you have a permutation like this, then when you do this conjugation, you do get a permutation in your normal subgroup that is a 3-cycle. So how else can the permutation end? Well, we can now assume that all the cycles have length at most 3. And so one case you could have happen is that your permutation ends in 2 3-cycles. Let's say A, B, C, D, E, F. Then you can check that if you compute sigma inverse times ABD times sigma times ADB, note that this is the conjugate here, then you will actually get a 6-cycle. Or correction, a 5-cycle. And lo and behold, that can be handled by the previous case. So you do this conjugation, you get a 5-cycle. Now do the conjugation from the previous case, and you get the 3-cycle. So congratulations, n has a 3-cycle. Note, I'm not actually doing these calculations because they're quite tedious to do. It's worth pointing out, because you have these disjoint cycles that have nothing to do with the elements you're interested in, when you're doing these calculations, these other cycles just pass through and cancel out with their inverses. So the only ones that actually end up mattering are the ones that I actually give names to. Alright, so if you have at least 2 3-cycles in your permutation, then you can construct a permutation in your normal subgroup that is a 3-cycle. So now suppose that we're not in that boat. So what can happen? It must be the case that these are all a bunch of 2-cycles, and then you end in a 3-cycle. Well, don't be silly, just square it. These are all disjoint, so they commute. They're all 2-cycles, so they go away when you square them, and you just end up with ACB. So that case was easy. Alright, so if you have exactly 1 3-cycle, it's easy. If you have at least 2 3-cycles, we can reduce to a case where you have a long cycle. And if you have a long cycle, then you can construct a permutation that is a 3-cycle. So we're now down to sigma is nothing but a product of disjoint transpositions. An even number of them, by the way. one thing you can do is conjugate by ABC. Do the usual sigma inverse conjugate by ABC, sigma ACB, and what you'll end up getting is ACBD. So, oops, you don't get 3 cycles by doing the same trick we've been trying to do. Instead, you get this condition. But it's still progress, because it's possible to still get down to a 3 cycle. And in fact, this case is kind of interesting, because if you're working with A4, this tells you that if you have permutations of this form and you conjugate, you start to get permutations of this form. It starts to give you hints that the Klein 4 group exists as a normal subgroup. And actually tells you why this proof fails when n equals 4, because you get to this case. So now we need to rely on the fact that n equals 5. We need an element that's not on this 4 cycle. We know that the element E exists. Namely, now you just take ACE, conjugate it by this permutation we just got, and then multiply it by the permutation we just got, because it's its own inverse, and you will discover that we suddenly get a 3 cycle. And so, when n is at least 5, it's possible to get from two cycles to a 3 cycle. And you see why I have to do this in 2 steps like this, because in order to actually guarantee that this trick works, I needed a 5th element, but I also needed to guarantee that the permutation was fixing that 5th element. And the only way to do that was to make sure to get rid of the other transpositions first. And as you can tell, I'm skipping a lot of details, which tells you why the textbook decided not to take this approach, because it's a lot more computationally intensive compared to their approach, which is a lot simpler.